Good morning. Yes, I am. How are you, Sean? How's everybody? Thank you very much for joining us this morning. I haven't been on air for a while doing a tech talk. I started a solar webinar on Tuesday, and that was my first foray into webinars for a good couple of months. So I'm quite rusty still. But this morning's short and sweet. As we know, it's a tech talk. It's 20 minutes, and then we're done. And then 10 minutes for questions, and hopefully we'll be out of here by past. So I was asked to do something on lagging because, as you know, tech talks cover subjects that are often that are surrounded by a bunch of questions and sometimes misunderstanding and so on and so forth. So I think it's tech talks particularly are things that drill down into details. So for example, I would mention lagging in a heat pump series or a solar series. Very briefly, it would be one slide or two slides, perhaps. This drills down into a little bit of more detail, hopefully to give some understanding as to why we need to take it a little bit more seriously. And granted, as a trade in this country, we've only been sort of asked to really notice it since 2011 or so, and it's been a new introduction almost. You can say that, although it's not new to the standards, but it's been a thing that a lot of focus has been put on it for the last couple of years. And there's still a little bit of confusion out there. So let's have a look at lagging, why it's necessary. For us to understand the need for lagging, I think we need to understand a little bit about heat and heat loss, and how does heat move and transfer itself from one place to another. Now, there's three main sort of types of heat transfer, ways in which heat move. Now, ways in which heat move. That is conduction. Conduction takes place through a solid material, whereby one molecule heats up because of the heat source on one side of it. It then starts to move more rapidly, and it excites the molecule which is next to it. The molecules themselves stay where they are. They don't move around. Well, they do. They vibrate, but they don't move around and swirl around like they would in a liquid. So conduction is transfer of heat from molecule to molecule in a solid. Convection, on the other hand, is what is happening inside this pot of water. So the water itself is conveying heat from where the source is, i.e. the bottom of the pot, where it's getting heated up, and the molecules themselves are then moving around and swirling around the liquid, and essentially they become they push themselves further apart because they become more excited, and their density becomes less. So we all know that hot water rises, and that's how it gets to the top. But and so that's convection, where the molecules themselves actually move around. And then you have radiation, where and radiation is actually the source of heat that we harness when we install solar systems. It's a heat that you can feel on your hand without having to touch the actual plate of the stove. It is this discernible heat that you can feel, which is radiated through the air. So those are the three main types. If you look at a normal copper pipe, how is heat going to be lost in a copper pipe, or any pipe for that matter? Conduction. Well, yes, you're going to have conduction. Remember, the water inside the pipe is hot. Copper is an excellent conductor of heat, so you will have conduction through the copper almost immediately to the outside surface of it. So immediately the outside surface of that copper pipe will become more or less the same temperature as the water within it. Convection, will you lose heat from convection? Well, yes, because air comes into contact with the outside surface of the pipe. it then moves away. It picks up some heat, it moves away, and even if it isn't moved away by wind or whatever the case may be, as it heats up, we know that it's going to become less dense, and therefore it's going to change its position. It's going to want to move upwards. And if you have a look at something in the distance, and you're looking at something through the top of a charcoal fire, you'll see that shimmer. You'll see that the haze almost. Your vision is blurred because you're not looking through flames. There's no flames, but what you're looking at is the heat and the air, which is rapidly moving and being forced to rise because of the heat. So exactly the same thing happens when air comes into contact with a hot surface such as a copper pipe like that. You will have convection, and you will certainly have a certain amount of radiation. So all three of those methods will result in heat loss from a pipe. And now we're looking at copper as an example. It's a common pipe, but some of the queries we've heard and sort of arguments that we've heard is that multi-layer pipe, for example, has sufficient thermal resistance properties so as to not have to be lagged. That is not the case. A multi-layer pipe is not as conductive as copper, I'll grant you that, but it most certainly does conduct heat outwards, and it will experience massive heat loss just the same. So although we're talking about different pipe materials, there is still significant heat loss through the outer surface of the pipe. Okay, so if we can agree on the fact that there's heat loss through a pipe, that's great. And just to show that fact, or to prove that fact, here's just a few little thermal images of pipes surrounding hot water cylinders, and some, like in this case, the top right over here, a shutoff valve, which is not necessarily close to the hot water cylinder, but probably part of a hot water line or a loop, a primary loop. And you can see from that all arguments of the heat loss through pipes is insignificant fall away completely. You do lose significant amounts of heat through pipes, and I will just reiterate the fact that you don't need flow through the pipes in order to lose the heat. It's not only when you're using hot water. So let's just think of an example of a solar or a heat pump installation. Both of those installations have what we call a primary loop. So they have loops which run to and from the tank and to and from the in a solar, the case of solar, it's a panel. In the case of heat pump, it's the pump. And so from time to time, those loops, the job of those loops is to carry hot water from the source of it and bring it to the storage. Now, to not lag that is you're almost cutting the legs off of the oak and asking to run a marathon. You're taking one wheel off a car and tuning it to go and do a Grand Prix. It's not going to work. So primary loops are one thing, but let's talk about stagnant heat losses and standing heat losses on stationary geysers. When I say stationary, I mean geysers that are standing overnight. Nobody's using any hot water. There's no water flow. So this image on the left here, you'll see that somebody is obviously using water. The entire pipe is warm. Likewise on the one lower right. But if you take a thermal image, and I'll show you next week, because this, by the way, this lagging webinar is in 2 parts. And I'll show you a thermal image of a standing geyser. That clearly shows that heat loss through a standing geyser is significant. All the pipes that come into contact with the geyser itself, then there's 3 of them usually. We're not talking about the primary loop or the other ports for the primary loop. You've got a hot water outlet, obviously. You've got a cold water inlet, and you have a TP discharge pipe. Those 3 pipes light up like a Christmas tree when the thing stands overnight. And this is what we're trying to prevent, and this is why we need to install. But I digress. That will be covered in a little bit more detail next week when we look at installation and protection and that sort of thing. For this week, I want to just drive home the fact of how necessary lagging actually is. Okay, so how does lagging help this? Well, let's have a look at conduction. Lagging won't prevent the conduction from the water through the pipe wall. Your outer surface of the pipe wall will still get just as hot as it was without the lagging. However, convection, when we look at convection, now it starts to help, because what did we say? We said when air comes into contact with that outer surface, it wants to naturally move away from it and carry that heat away from the pipe. So now all of a sudden it can't do that because the lagging protects it. The outer surface of the pipe, it will prevent air from, first of all, well, certainly air comes into contact with it. It's there, it's trapped. It's a closed, this particular type of lagging is a closed cell type of lagging. And so, but it doesn't allow the air to escape. Okay, so it certainly helps for convection and radiation likewise. So you can, even though on a very, very hot primary loop, if you go and touch the lagging of that primary loop, yes, it is warm. It's not perfect. Nothing's perfect. You'll have to put lagging a mile thick for it to be perfect, but it certainly is a hell of a lot less radiation coming from the pipe than it would have normally been. How think of, I sat wondering how to visualize what lagging actually does to prevent heat from escaping, and I thought of the following. Think of why sweatsuits are effective at trapping heat. Now, if you want to have a sauna experience without having to invest in a sauna or go to your gym, buy a sweatsuit and go for a run. What does that do? It doesn't allow any air in or out. At the same token, breathable clothing like the cyclist shirt are excellent at allowing you to feel cool even when exerting yourself. So what do these things have in common? They take advantage of one singular phenomenon, and that is airflow. Airflow is the thing that allows our bodies to remain cool, and it's the thing that allows heat to be removed and robbed from pipes. So airflow is the thing that we're trying to prevent essentially. There are other, like radiation is another thing that does get curbed, but airflow is the thing. So essentially the lagging traps the air and so prevents it from removing heat from the pipe, and it's as simple as that. So it would then stand to reason that various thicknesses of lagging have differing performance values, right? And that's where the R rating comes in, and we'll discuss that in a little bit. Now, let's just briefly look at the common types of lagging. This isn't all the types of lagging. In this country, let's be honest, we use a little, these kinds, glass wool and rock wool are types that will be used more in industrial and commercial applications where the lagging and pipe insulation has been spec'd by engineers, and it's almost like a subcontractor's job to do and come in, and it's a hell of a big thing. And yes, but I've seen many domestic installations with both rock wool and glass wool insulating the pipes, and these are both excellent lagging systems. I've seen them both in domestic installations. Most of where I've seen them have been older installations. I think it was a little bit more common maybe 20 years ago, and it's still perfectly good. Usually not usually. As you can see here, these two examples here have got one single split. You open it up slightly and you put it over the pipe. Rock wool, something like that, you go onto the website, have a look, and they will say to you, use binding wire every 20 centimeters or so, tie it off, and if you like, you can wrap it up if it's outside. But essentially, once you've bound it like that, others with this aluminium foil around it, which is already protected, you could use this sort of sealing tape, and some even come with a taped strip which has got a peel back thing similar to that, and it's an overlapping piece of tape which you peel you peel the backing off, and it's a self-sealing system, and that's reasonably common here. But by far and away, the most common type of lagging that we come across in South Africa is these closed cell foams, nitrile rubber, and that sort of thing. So this is the kind of thing that we, as inspectors, as auditors, like to see. Not that the previous is we'd love to see the previous, but it's sometimes just unrealistic, and labor-wise, it's a hell of a lot more intensive, I believe. So this is the most common one that we come across. And just to show you that, because if any of you have ever been called up on lagging on one of your installations during an audit, and something, a comment like, well, the joints and T pieces were exposed. So when we talk about mitering and covering the joints, we'll see that next week. But there are products like this available that are able to close and seal up joints and seal up miters and all the rest. So there's no real the products do exist to do the job properly, is what the point I'm trying to make. Okay, let's talk a little bit about R value. Now, this is a buzzword that everybody's heard, and a lot of people are unsure about, and it is, I admit, a tricky thing to wrap your head around, because there are varying stories out there. So let's just look at the very, very basics of R value. So I'm not going to delve into the calculations because I'm not a maths oak, and I will get it completely wrong. So the R in R value refers to the material's resistance to heat flow. That's why it's called the R value. So it refers to how resistant the material is to heat flow. If I put this material in an environment where to the left of it is 20 degrees Celsius and to the right of it is 10 degrees Celsius, how much resistance will it have to prevent the heat flow from the higher temperature side flowing through it towards the lower temperature side? That's what the R refers to. Now, how do you get an R value? So the greater the R value, let's just get the hierarchy right. So the greater the R value, if something's got an R value of 1, it is 1. If it's got an R value of 2, it has a greater resistance than the R1. So if we say R1 is a requirement, and we can show that in fact the lagging we've put on is R1.32, then we have exceeded the requirements. Okay, so the greater the R value, the greater the resistance to heat flow. Second law of thermodynamics dictates that heat will only ever flow from something hot to something cold. It'll never flow the other way around. So the prevention or the direction of heat flow from a pipe will always be from the pipe outwards, and we're talking about hot pipes here. Okay, so I'm not talking about freeze protection. That's obviously a different story, or well, in fact, it's the same thing, wouldn't it be? Yeah, it's the same thing, because you still got heat flow towards the outside. But so I'm not talking about refrigeration lines and cold lines where the heat flow would be trying to get from the outside in. We're talking mostly about hot lines where the heat flow is trying to get from the pipe outwards. So it'll always, for our intents and purposes, be in an outward direction. That's the second law of thermodynamics. It'll never change. And that doesn't really matter. But okay, so let's just look at the R value calculation. How that is done, you need to first establish the conductivity value of the material. So different materials, you can have a lagging material like rock wool, for example, and I don't know the figures for the various materials off the top of my head. Let's say rock wool's conductivity value is better than or it has less conductivity than nitrile rubber. It would mean that you would need less of it to do the same job than the nitrile rubber. So thicknesses do come into it, and we'll get to that in a minute. So various materials have differing thermal conductivity values. It is the value given to a material to measure how well it conducts thermally. Something like copper, for example, will have excellent thermal conductivity values, and it'll be off the charts. And that value, or a K value, is given as in watts per meter Kelvin or watts per meter degrees Celsius. A Kelvin And a degree Celsius, by the way, is the same thing in terms of size. It just they just offset one another by about 280 degrees. So 0 Kelvin is minus 280 odd degrees Celsius, and that's so. But in terms of a degree, 1 degree Kelvin, 1 degree Celsius, they're the same size. So the thermal conductivity value of a material is given in, or the K value is given in watts per meter Kelvin, and that is in the international system of units which we use in this country, which Australia use over there. It's called abbreviated to SI, and that is important to note. Plant that little fact in the back of your mind. Note that a material with higher heat conductivity will have a lower R value, because if you have a higher conductivity, it won't be as good at preventing heat from flowing through it. Does that make sense? So I'm going to skip this third paragraph. I'm going to go to the fourth one quickly. Once the thermal conductivity or K value is known, the results can then be used to input into a calculation to calculate the R value as per the following test. Now, once you have the thermal conductivity of a material and you know how fast heat travels through it, you can then easily use that info to calculate the resistance value. And that's just an R value to simplify things. And we know that we want R1, or this specified R1.5, or that specified R2. And so we have a simplified methodology of knowing what sort of insulation we need. So R value is a product of a function between how well a material conducts heat through it and the thickness of that material. How much of that material do you need to achieve a certain amount of thermal resistance? And that's the value we're worried about. Now, I'm going to go back to this third paragraph here. There are many products out there, and you can browse the web today, and you will find products that are 10 mil thick, 8 mil thick, and they will have an R value of 2.2. Now, the American measurements for R value are done in imperial units. It's the same system as the British use with the BTU in that. I don't even know what BTU stands for. Something. I don't want to confuse myself. So they use imperial units, and the net result of their R value measurements are nearly 6 times higher than the units we require here and the units that we use here. So when you see a thin little lagging and the R value is 2.2, forget it. That's the American imperial units measurement, which is 100% fine for them. So they will require an R value, for example, on pipe lagging of R13, let's say, okay, or R10. So don't confuse the two. Don't just look at R value and think R value is R value across the globe. It's not. We use SI, International System of Units, and the Americans use imperial units. So there's two different types there, okay? So to put it in a nutshell, for pipe insulation to achieve the minimum required R value of 1, and that we all know is the minimum requirement, using typical expanded nitrile rubber, which is those tubes that we're all familiar with a thermal conductivity of 0.038 watts per meter Kelvin, as an example. By the way, that is the thermal conductivity of expanded nitrile rubber. The following common thicknesses should serve as minimum requirements. For 15 and 16 millimeter pipe OD, requires lagging of wall thickness 19 millimeters. Wall thickness 19 millimeters. 22 millimeter pipe OD requires lagging of wall thickness 21 millimeters. Now, I'll refer back to the fact that this is an example using nitrile rubber, expanded nitrile rubber, those Armaflex, gosh, help me out with a couple of brand names. You know, the black tubes that you buy. And those are the ones. So the wall thicknesses there are pretty well known. So as an auditor, you'd go to site and you'd easily be able to see whether one, you know, whether the lagging complies with, you know, as you know what I'm trying to say. Sometimes I lose my train of thought. So here's 4 examples of lagging, and only one has the required R value, and that's this one. So at a glance, one can very, very quickly tell which pipes have been lagged correctly and which comply and which don't. So this is a very common sort of a size lagging. This is less so, and we've all seen that. So the requirement, the R requirement in lagging is a non-negotiable. It is something that it's dictated by the standards, and it is something that is quite easily detected. At a glance, an experienced eye will see immediately that this is not R. And that's it. So next week we'll look at installation of lagging and the protection of that lagging. And yeah, I'm hoping that'll be just as lucky as this week was. Thank you very much. And that's it. That's me.
All right, perfect. We do have a couple questions, so let's get straight into it. The first one reads, is it necessary to insulate a hot water ring feed with Pexal pipe? And why did some geyser manufacturers go back to 400 kPa? Is it because of more insulation and to save weight?
Okay, two questions there. The first one is, the answer is unequivocally, absolutely, 100% yes. That is one of the biggest heat sinks in a plumbing installation. You can imagine the amount of heat lost through a ring main, a hot ring main, no matter what kind of pipe it is. That thing has constantly got hot water circulating through it. So if you do any less than insulate that thing perfectly well, you're doing the client a big disservice. So the answer to that is yes. Second question, I don't know the answer definitively, as I'm not a manufacturer, but I would guess that it was in the interests of longevity. I know that certain manufacturers have upped their warranties from 5 to 7 years, and in trying to, I would guess, trying to preserve or conserve or increase the longevity of the product, they would drop the pressure down to 400. I don't personally think that 600 is necessary in a home. I think 400 is perfectly good, bearing in mind that I'm talking about a home that is being plumbed and the pipes that have been sized correctly, because we often assume that half-inch multi-layer piping can be plumbed through an entire 6-bedroom home, and that's when you want the big pressure, so you can force the water through. No, it's not how it works. 200 kPa is more than sufficient if you pipe it properly.
All right, perfect. The next question reads, as plumbers, we prefer using Gerber-Mepler pipe everywhere possible for water reticulation. But if installation requires copper tube, how can one prevent the colorization turquoise to sanitary ware or tiles in the shower in the long term due to water that exists on taps coming directly from the copper tube reticulation?
I'm not sure I understand that fully. I think, could that person email me with that question? I'm not sure I understand the question fully.
All right, perfect. The next question reads, are all lagging SABS approved?
No, not. No. The requirement for lagging is that it must be R1. And there are a couple of other things that we must do as installers that we'll have a look at next week. And I must be honest with you, I should have done my homework, but at this point in time, I'm not sure whether there exists an SABS requirement or product standard for this, for the stuff, beyond the fact that whether it's R1 or not. I'm sure there does, and I don't know what that is, what the actual number of that standard is. I'm writing a note as we speak, and I'll find that out.
All right, perfect. Just on that last question, we have got a comment from the audience that it reads, we have no national standards. We adopted AUS standards.
Yeah, I would tend to agree with that statement. ASTM, I think, is the thing. Yeah, quite right. We adopted a lot of Australian standards.
All right, the next one reads, warning, why was the inefficient lagging used in B-rated geysers, i.e. was it necessary to increase size and the spec of the lagging surrounding the tank R1?
Yeah, look, B rate, the rating of the the efficiency rating of a geyser as it relates to R value of lagging, I'm not sure of that correlation and where that fits in. I would hesitate to say that the lagging or the insulation material around a B-rated geyser is inferior. I don't know. I'm not a specialist in that field. I really am not. So I don't know whether it's an economic thing, whether it's I know that they use that expanded foam that you spray in, and for the steel tanks, and copper tanks are also having to look at that technology, because the little polystyrene balls that they use between the copper and the outer tank traditionally will never result in a B-rated geyser. So that's a problem for them. So they're having to look at expanded foam as well. I don't know if it's inferior though. That is out of my area of expertise. I really would have to approach manufacturers for those answers.
All right. Next one reads, is lagging installation compulsory?
Yes, it is. Around the geyser, the first meter of pipes surrounding the geyser, TP, cold in, hot out. But then it also becomes compulsory on the entire hot water reticulation. All the pipes that are exposed in a hot water reticulation system need to be lagged. This is, we're talking new builds and new homes. If you come across Mrs. Jones's existing house, you're not obliged to do it, but you are obliged to tell her that it's not done. So again, disclosure and non-compliance notices. So yes, the standards do call for complete lagging of all exposed hot water lines.
All right. The next one reads, can you use any lagging that is 19 millimeters and 20 millimeter pipe? The lagging is 22 millimeters.
I would almost want to say you can, barring one or two things. So look, the thickness for us as auditors is just a sort of a yardstick. Okay, it's not a definitive yes or no. It's a yardstick. So our suspicions are raised if we see thinner lagging. So we will ask the question, and then the onus will go back onto the plumber to show that this particular lagging he has used is in fact R1 rated. It might be an exotic material that I've never seen or heard of, and I get educated, and I'm happy for that. But I will still ask the question and say, I don't know what this R rating of this, I'm not familiar with it. Please show me the calculations. Please show me the spec sheet, and that'll have to then prove the case.
All right, perfect. The next question reads, I'm pretty sure you've answered, but I'm going to ask it anyway. Isn't it the plumber's obligation to only install and use SABS approved products?
Yes, it is. As I said, I'm not sure to which extent SABS sort of rated or proved lagging is out there or available. I would almost argue that it's a critical part of the installation, but if it's of a sufficient quality and it meets the R requirements, and we install it properly and we take proper care of it, I would be hard pressed to come down on that plumber and say this isn't SABS rated stuff. You can't use it. You know, the SABS rating of components and pipework and that sort of thing more is for me big value. It resides in the pipe, in the fittings, in the geyser, in the valves, etc. Those sorts of things that can catastrophically fail. But the lagging, as long as it's fulfilling the requirements, I would not make a big fuss about it.
All right, perfect. Well, that's all of the questions we have got. We have just got a comment that reads, BTU stands for British Terminal Units.
Thermal units. That's right. Yes, British thermal units. And they measure that in it's a measurement, or it's a product of how many joules it takes to heat a pound of water by 1 degree Fahrenheit, and that's how that works, I think.
All right, perfect. The next question reads, what to do if R1 lagging is not available at the time of installation, as the lagging is not always freely available?
Yeah, look, I mean that's a question that'll always crop up. Yeah, I don't know if this is the forum to answer that, and that's a whole story. So, you know, suffice it to say that this little webinar is about what the requirements are. If you can't get R1 lagging, I mean, to me, it's not always freely available, but if it's absolutely impossible to get, and you can show that, and then perhaps just just take the necessary steps. I would try and make a plan to get it, or suggest an alternative, or perhaps double up on the thing, or I don't know. But I'm very reluctant to say, no, go ahead and use a lesser thing and just write a notice of non-compliance. I think that's the that's what the question wants me to say. But I'm reluctant to say that. I think that if we make a little bit of effort, we can make some plans to get some R1 lagging. I know that there are a couple of suppliers, and the more of us that put pressure on suppliers to stock the stuff, the more it's going to become available.
All right, perfect. We've just got a follow up on that from the audience. It reads, there are other materials without SANS standards. See 10252-1 normative references.
Normative. Okay. I'll have a look at that as well. I'm not. I certainly accept the fact that there's going to be many types of lagging, many materials that will have the required R1 rated, and it just means that the engineer, the resident engineer, the architect needs to do the calculations, use the thermal conductivity measurements of that material, plug it into the R value calculation, and show that a particular thickness will work for a particular thickness of pipe, and everything's good. So there's there's nobody trying to catch anybody out. It's and when nobody's saying that you can only use this or you can only use that, as long as the rating of the insulation is R1, and that's the minimum requirement for pipe insulation. So I'm sure that there are many fantastic. You go onto a website like Armaflex, they've got half a dozen, probably a dozen different types of insulation material there, all with different values. I suppose it becomes an economic thing as well. Affordability.
All right, perfect. Guys, it is almost getting to the time that we do have to end off the session, and questions do keep coming in. If we are not able to get to your questions, guys, that you have posted on the system, just go ahead and just give us a day, and we'll try and get back to you via email. But guys, they all keep coming in. I have sent Richard's email through the chat. I know he loves corresponding with you guys. So if you do have those questions, just drop an email there. But Richard, the next question reads, and I do think it will be the last question. Insurance supply 1 meter pipe with geyser vacuum breakers and PRV valve. Whose problem is it if we replace geyser for client and the lagging and stuff like that supposed to be added?
So between the insurance industry at the moment and see, there's this thing called betterment, and the insurance industry won't necessarily make the installation better than it was. So their mandate is to replace and bring the client into the same position as they were before. And the fact that lagging is not considered a crucial safety element or factor, the generally accepted practice now, and I don't want to encourage, I don't want to say that this is just the end of the story and it's never going to change, because we're defeating the whole object. Of course, the object is to try and get all systems compliant. So the generally accepted methodology now is to make the client. So a couple of things need to happen. The client needs to be told in no uncertain terms that this is non-compliant, that you need to install lagging, and that it's going to cost you $1,000. And the client is either going to say, yes, please go ahead, or no, thanks, I can't afford that, go away. In which case you must have issued her or him in writing with a notice of the non-compliance, stating what the problems are and saying that I've suggested this to you and you've told me to go away. The onus then falls on the homeowner. And the next time that insurer comes to replace that geyser, they can then start to ask questions and say, hang on a second, but you were told about this 3 years ago and you still haven't done it. Now we're going to start asking questions about the longevity of your system because you haven't, or whatever the case may be. I might be talking nonsense, but I'm saying that at some point in time, pressure needs to bear on somebody to rectify situations, and lagging is no different. Although at the moment, an insurance plumber, insurance tank geyser replacement doesn't have to, in making it better, doesn't have to install lagging. They can just issue a notice of non-compliance. I wouldn't like to see that perpetuating over the next 10 years, let's say. I want to see that at some point somebody takes responsibility and says, okay, let's put the lagging in here, guys, and who's going to pay for it, or whatever the case may be. So, but at the moment, that's the story.
All right, perfect. Guys, that is it. I am going to end the session off. It is now 20 minutes to. Thanks so much for joining us this morning, and please remember the survey on the way out. Thanks so much, guys. I'll see you next week Thursday.